All right, let's continue. And now we're going to go back to collisionless dynamics, right? Now, it's going to be a little bit more schematic, perhaps, because we can't go through all the details in the realm of this course. That would be a dedicated course in stellar and galactic dynamics, actually. Now, the thing here is that the governing equation, as it were, is essentially this one now. I'm just going to see so I don't get it wrong in this case. I don't know it by hand. And this is the collisionless Boltzmann equation. Okay? Now, the collisionless Boltzmann equation is an equation for F here. And F is the distribution function in phase space, such that F in a differential volume, dx, dy, dc, and in velocity space, dvx, dvy, dvc, is the number of particles contained within that differential volume in phase space. Okay? It's the average number of particles, so on. So from this then, we can define the mass density as the typical mass of the particle times the number density, where the number density then is the integration over all velocities of the distribution function. So you integrate over the Vx, the Vy, the Vc. So this is really then a triple integral, of course. Yeah. Now, similarly, you can use this also, this definition, the other, to define the various velocity moments, whereby two of them will be important for us here. The first is just then the integral of f and then weighted by f, and now I will just say the 3v here, which is just to take the Vx, the Vy, the Vc, okay? Just to say same sum. But this we know. Divided then by the integral there. So you can see that this is essentially the velocity average, right? The velocity average of the distribution function, okay? And of course, you can also formulate this in terms of the mass and the number density of the particles, because this is just that. Similarly, the next moment, VA, Vj, is then F, Vi, Vj, d3v, and then again divided by this one. So typically this, of course, has to do with the number density that we associate, the mass density. This has to do with mean velocities, and this has to do with velocity dispersions. Okay? This. So if you now take the first moment of the collisionless Boltzmann equation, and I'm just going to do it in 1D along x here now, because it's simplifies the notation. And then I just identify the mean velocity with Vx here, because I just take it in 1D. Plus V dx V equals to dx of the gravitational potential then, minus 1 over n dx n sigma squared. Okay? Where now this sigma squared is just v squared minus v squared, and that is then the one-dimensional velocity dispersion. Okay? Now, this is called the Jeans equation. And it is the analog to what we had before the break if we took the momentum equation or the Euler equation of hydrodynamics when we kept the velocity field. So setting v equals to 0 here would then deliver the equivalent to the hydrostatic equilibrium equation. And what can we see? Well, we have something. We could have formulated this in terms of the mass density, right, instead of number density. Then we have something which is the same in form. We can do this for the full Jeans equation, but we could also take the simplified case of hydrostatic equilibrium, so mean velocity is 0, right? Here, what do we see? Well, here we have the gravitational potential, which is balanced by this term, which is 1 over rho, and then we have d dx of rho sigma squared, right? So, if we compare this now to what we would have in hydrostatic equilibrium, then we have the phi, the x in this case, right, was minus 1 over rho, let's just call it minus 1 over n now, and then we had the p gas, or the p tut really, the x, right? So in this case, we can see that this term, n sigma squared, right, acts as a dynamical pressure, okay, in the collisionless Boltzmann equation. Well, in the Jeans equation, the first moment, right? So, we can save a little bit, but we can already now actually take this already from this equation a little bit further by the analogy directly there, that, all right, but we consider hydrostatic equilibrium before, right, on this form, and then we put Pg as essentially, say, the density, right, times a squared. So if we formulate this in terms of the mass density here now, so we just multiply, and then we have the mass density there, then we can see that indeed the dynamical pressure term has the same form. It's a density, so rho or n in this case, rho times sigma squared. So as we will see when we officially introduce a Maxwell distribution into this later, we will see that they come out, as you can sort of see here, that A, the isothermal sound speed, can be identified with sigma in this case, right? And this is indeed the analogy that explains a lot of terminology that we may also encounter in various situations where we have this type of collisionless dynamics, stars moving around in, say, a disk of a spiral galaxy. Often people are talking about in the literature of a hot disk or a cool disk. And a hot disk here means that the stars have high velocity dispersions. The analogy is with this, that it is sort of a thermodynamic temperature in this case, just as the isothermal sound speed depends on the temperature, as we know, right? So the higher the velocity dispersion, the hotter the disk, the higher the temperature. And similarly, a cool disk will then mean that the velocity dispersion of the stars are low. And we have a cool disk. And we can take it even further, because if we think about collisionless dark matter particles, then we can think about, okay, hot dark matter particles. What are they? Well, they are dark matter particles with high velocity dispersions. Cool dark matter particles. What are they? Well, they are dark matter particles with low velocity dispersions. So C in your CDM, cold dark matter, comes from that. All right, that was just a little bit illuminating, hopefully, in terms of how we use this terminology. Now we will move on here to some specific systems that we will consider. All right, first, we're going to do a spherical symmetric model, okay? That is, we have this in r, theta, and phi, right? So that's a spherical system. And if we assume that it's stationary, okay, then we directly have the conditions that the mean Vr has to be equal to the mean V theta, which has to be equal to 0, because otherwise it wouldn't be stationary. Okay, if the means were different, we would have regression. We could still have a V phi, right? We could still have rotation. Okay, in such a situation. Otherwise, flows would occur. Similarly, for the anisotropic terms, Vr V theta has to be equal to Vr V phi, which has to be equal to V theta V phi, which has to be 0. So that's for the various velocity dispersion components. So we're left with essentially that we can have some rotation of the system, and we can have the 3 dispersions in this dynamical situation. Now, if we again now assume spherical symmetry also, then of course we cannot have the rotation, so that will have to be 0. And furthermore, by symmetry argument, we must have that the dispersion in V theta and V phi are the same. And with the stationary condition then, this is also then 0, of course, and then we can write down the only non-zero component of the Jeans equation, which now is the radial part, as, and now I will use the density instead of the number density there, rho Vr squared, and then we have plus 2 beta divided by r Vr squared equals to minus the phi, the rho, where beta then is 1 minus V theta squared divided by Vr squared, okay? And that is then, you could do actually the same exercise for the Euler equation. This is the anisotropy parameter. So what does this mean? Well, it means that, of course, if beta equals to 0, then all 3 of the dispersions are the same. So we have isotropic velocity dispersion, right? Because then all the 3 are the same. This must be equal to that. And by definition for this system, we had that V theta squared has to be equal to V phi squared, right? So then we just have that. Now, we can also see that, okay, what if we only have radial orbits, right? That just goes like this. Then only this one is non-zero. This one is 0 and beta equals to 1, that corresponds then to radial orbits. And beta goes to, well, minus infinity. That then corresponds to only circular orbits. Only the dispersion in v theta or equal to v phi are 0. Now, the reason I bring up the beta parameter already in this lecture is that it is often inferred to be the case that elliptical galaxies are not spheres, they're elliptical, they're flattened, but they're not flattened primarily, it is believed, due to rotation. Remember, rotation in a general sense for elliptical galaxies are low. They are instead flattened because the velocity dispersion is anisotropic. That is, it's not perfectly orbit, and that's actually what flattens the elliptical galaxies, rather than rotational flattening, as for the disks of spiral galaxies, for example. Okay? So that is one place where this is very important then. Now, in general, you can see that the Jeans equation here now contains two unknowns, beta and dispersion, but it's only one equation, right? So we're short of one equation, which makes it difficult to solve. You often have to do some sort of either try to get some empirical constraints on the beta, or assume something, assume a model, try to calculate the model in order to then solve it. We can obtain solutions, though, that we can discuss here by, again, assuming that we are isotropic. That is, that beta equals to 0. Okay? So we will assume that and take this part away. So we're left with this equation here now. Okay? So this now then corresponds to a model where we have assumed a distribution function on the form. Here is a potential minus the kinetic energy there. Okay. Rho 0 divided by m, so that would be your n, right? Divided by 2 pi sigma squared 3/1/2 e to the minus phi minus v squared by 2 divided by sigma squared. And indeed, we recognize this as our Maxwellian velocity distribution for the velocity dispersion sigma. We can go back to look at our Maxwell-Boltzmann distribution that we had during the fall, and we will see that they have the same form, right? So if we now look at the Poisson equation again then, and use this form, then the Poisson equation gave us 1 over r squared, right? D dr r squared d phi dr equals 4 pi g rho. Okay? Now let's use that one and equate the r squared to sigma squared. the velocity dispersion in this case. Then we can, again, hopefully, reformulate this if we say that this velocity dispersion, again, is a constant. So we say that this velocity dispersion is constant, such that when we now replace the gravitational potential here with this equation there, right, we get out something which again has the form d dr r squared d ln rho dr equals to minus 4 pi g rho divided by sigma squared. And again, you can see that this is identical as what we had before the break, but where we indeed have identified that the velocity dispersion now is equal to the isothermal sound speed, which we of course know is kT divided by mu mh. So hence again, this analogy between the collisionless gas dynamical model and the collisionless dynamics model and the gas dynamics. So this gives the same structure. The density structure here is the same as the self-gravitating sphere. Yeah? We can insert the same singular solution, and we will have to do the same modification at the lower boundary in order to get rid of the cuspy core of the model. Now, I did mention, and we can introduce the same scaling radius, the King radius, as we did before the break. I did mention that this can be usefully can be made more useful also at large distances, and to avoid the infinite mass problem by truncating the distribution function. Okay? I had to look it up in the notes because I don't know the exact expression analytically here now. But if I denote by epsilon this term that I had before, which was the gravitational potential minus v squared divided by 2, right? Then we can say that the distribution function for epsilon greater than 0, yeah, that is that when you are still bound, okay, if you have two high velocities, you're flying out. This was the evaporation effect that we talked about before, right? But once you are above there, then you follow the distribution function here, which is just slightly modified. Minus 1. And then if the distribution function for lower there is just 0, then you have escaped. Then again, you can derive an analytic approximation for the density, which is just this one. We know this is just then there, then v squared dv. Okay? And you can also then use the integration. You can formulate this in terms of the density. You can formulate this then also in terms of the gravitational potential phi, and you can insert the same lower boundary conditions as before, that is the rho, the r equals to 0 at the lower point, or the phi if you do the gravitational potential. The phi, the r equals to 0 at that point. Okay, that was what gave you this curve. Remember, in the rho divided by rho 0, we truncate, so we don't get the Cuspic core. But then now we have a modification also at the higher radii, such that the drop-off becomes then steeper. And that steepness then you can evaluate, and there might be that we will do this in some sort of exercise at some point. At a radius called the tidal radius. This tidal radius is then a concentration of the King profile, which essentially is the logarithm of the tidal radius divided by RC. And that's sort of a parameter that concentrates this. And essentially, you can try to identify this tidal radius where the position where the potential reaches 0. Yeah? So you have a vanishing density beyond that. Now, this is often also used observationally and not then related to the underlying model, but the tidal radius is simply where you assume that the galaxy ends observationally, right? Which we will come to during later classes. So I wanted just to give you one more example of analytical models that are often in use, and that's a specific example of what called a double power law, a broken double power law, of which there are several. Yeah, we will list them during a later class, a few of them at least. Now, one of importance that I wanted to mention explicitly is called the NFW profile after Navarro Frank White, and that is a analytical density distribution function of R, which has a core density there, and then R divided by RS, which is an either scaling radius then when plus 1 over RRS to the second power. So this has a 2 power law components, because in the inner parts here, yeah, it will essentially go with 1 over R, but in the outer parts it will start to fall off, as you can see, with 1 over R cubed. And that 1 over R cubed then save us in terms of the infinite mass, but the 1 over R is still what we call a Cuspic core. So a Cuspic core in this case is when you don't flatten it out like this, but you go up. Now the reason I mentioned this form here is that this is originally derived as an analytical fit to dark matter simulations. So these big numerical dark matter simulations that tries to calculate the evolution of essentially dark matter halos and their surroundings, typically find that in a dense dark matter halo, the density, in the dark matter halo, the density distribution follows roughly this form. And you can directly see that this is a certain problem, of course, because it basically means that to within very small radii within the dark matter halo, you still continue to increase with essentially 1 over R, right? And of course, you wouldn't do that until R equals to 0, because then it's infinite density. But it has what we call a cuspy core. A cuspy core is when you continue to increase significantly also in the innermost parts the density with a functional radius. And this lies at the root of the so-called cuspy core problems. That is, that this is a prediction of the models, but it's not really observed. If anything, it is observed that the innermost regions of the galaxies, they do not increase so steeply, less steeply, right? Now, one could make the argument that that is because the innermost regions of most galaxies are dominated by the visible components and not the dark matter components, so that it's only at the higher radii that dark matter components. So we can't really see this cuspy innermost regions. But there are actually also so-called low surface brightness galaxies, which are exactly what they seem. They are galaxies with lower surface brightness than a normal galaxy of the same luminosity, let's just say it like that. And they also do not seem to exhibit this type of cuspy cores, as far as we can tell from observations today. So this light is the root of the so-called cuspy core problem of the dark matter simulations of present day. All right. I think we'll leave it with that.